Yeah, we're going to pick back up where we were before when we were doing the second derivative of this implicit. We had already come through and we had done the first derivative and we'd found it to be negative x over y. And then we had started the second derivative and we were doing the quotient rule. So we had done the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which we had to do dy over dx. Then we did the denominator squared. Then we started cleaning it up. So we got negative 1 times y, which is negative y. And then we had the two negatives here made positive x. And then we substituted. So that's what we substituted there. Dy over dx became negative x over y. And so at that point, you do have to do a little bit of cleaning. So you've got y squared on the bottom. So the cleaning comes in when you do this little product right here. You've got to do x times negative x, and that gives you x squared over y. So you enter the realm of complex fractions, which is not awful, but nobody wants to stay there. So to get out of it, you have to take your small denominators and find your common denominator of those. Thankfully, we only have one. So multiply through by that common denominator. And when you do, y times the numerator here, y times negative y, gives me negative y squared. Y times this fraction right here, the y's cancel out, and you have x squared. Y times your denominator gives you y cubed. Okay, it looks a little weird, but you're trying to substitute again. So remember earlier we had that abundance of negatives. That's never a good thing. So factor out that negative, that gives you y squared plus x squared. Well, that should ring a bell because, excuse me, that's a 3. Remember the very beginning, I know it's scrolled off the screen, but the very beginning of this problem was x squared plus y squared equals 25. That was the beginning. We've got to use that to substitute again because we know that the sum of x squared plus y squared is 25. Well, we have x squared plus y squared right here. So we're going to substitute again. And that's going to finish us off. Because once we make that substitution, we've got our negative out here. We're going to substitute that sum for 25 with a denominator of y cubed, and we're done. Okay, it's just kind of lengthy. Y'all have got to remember how that goes. Okay, we're moving into related rates. You do have to read your problem and know which formula you need. The radius r of a circle is decreasing at a rate of 3 centimeters per minute. Here, hold up just a second because it's not showing up on my board. I can't see it. There we go. So let's try this again. There we go. 3 centimeters per minute. Find the rate of change of area when the radius is 4 centimeters. Okay, so we need, obviously, area of a circle. So A equals pi r squared. Yes, you're going to be required to know the formula. I'm not going to give it to you, so you're going to have to be able to determine which formula you need and pull it out of your memory. Now take the implicit derivative of that. dA over dt. We're always going to take the implicit derivative with respect to time when we're doing related rates. Okay, and so 2 times pi r dr over dt. And then we're going to come over here and we're going to list out all of our variables. dA over dt, r, dr over dt. So there's 3 things. One of them we're going to be looking for, and the other 2 they should have given us. It says the radius r is decreasing at a rate of 3 centimeters per minute. So that's a rate. So it's not the r part, it's the rate for r. So it's decreasing 3 centimeters per minute. Okay, so find the rate of change of the area, that's what we need, when the radius is 4 centimeters. So if we come in here and replace the items that they gave us, radius is 4 centimeters. The radius is decreasing at 3 centimeters per minute. What's going on? We have 2 times 4 times 3, so that's 8 times 3 is 24, and it's going to be negative 24 pi centimeters times centimeter is centimeter squared over minutes, which should make sense because this is how is area changing in comparison to time. So our unit should be area over time. So it should match. Okay, let's go to the next one and see what it's got. Again, I need to move it. So there we go. All right. It says the length of a rectangle increasing at a rate of 6 inches per, and let's do minutes because I don't know why I've got M. So minutes, and its width is increasing at a rate of 2 inches per minute. When the length is 10 inches and the width is 5 inches, how fast is the area of the rectangle increasing? So area of a rectangle. Area is length times width. Okay, that's product rule. So you've got to do implicit derivative, product rule. So length, and then we got to do width. So you have a lot of things to list out. dA over dt, and then it really doesn't matter what order you list them in. If you just want to do them in the order that you write them on the page, so be it, whatever floats your boat. You just want to have everything listed out so that you know what you got. Okay, so the length of a rectangle is increasing at a rate of 6 inches per minute. So the length is increasing. That's your rate of your length. Increasing, so it's positive 6 inches per minute. And let's just, put in minutes. Width increasing, so that's the rate of the width. So it's positive 2 inches per minute. And the length, we're taking a snapshot of when the length is 10 inches and when the width is 5 inches. Exactly what is the area doing at that particular moment in time? So we're just coming in here. We need to substitute and evaluate what's happening. So the length is 10 inches. The width is increasing 2 inches per minute at that moment. And the width is 5 inches at that moment. And the length is increasing 6 inches per minute at that particular moment. Multiply it out, we have 20 inches squared per minute. And then we have 30 inches squared per minute, for a grand total of 50 inches squared per minute. Which again should make sense because we're getting how is the area changing as time is changing. So it should be area compared to time. Okay, and the last one happens to deal with, it's still related rates, but it is a little bit more in depth. You are dealing with a cone. It is an inverted cone, and there is a typo in here. I corrected it on the review sheet. This should be 21, which will make this much more sensible here in a minute. When you put that in here, your height, 21, the entire diameter is 14. Now, that is good to note because if the diameter is 14, your radius is 7. Radius is 7, and then height is 21. What that leads you to know is your height is 3 times your radius. That is highly valuable information because we're having to do with the volume of a cone. Volume of a cone is 1/3 pi r squared h. Well, that's too many variables. We really need to consolidate. We've got to get some kind of relationship between R and H. And this right here is the magic formula. Now the question is, do we need it in terms of R or do we need it in terms of H? The question is answered right here. It says when the water is 10 feet deep. So that's talking about how high or how deep the water is. That's not talking about radius. That's talking about depth, which is in terms of height. So we need to solve for R. So get R by itself. So divide through by 3. And so R is H over 3. We need to put that into this formula. So if I do that, R is going to disappear. And I'm not going to have R anymore. And that was my goal. So I need to square the top and I need to square the bottom. That's going to be H squared over 9 times H. Okay, let's keep consolidating. There's a crazy wiggle on my board. So that's going to be H cubed. Oh, that's just ridiculous. Okay, try this again. 1/3 pi, and that's going to be H cubed over 9. Okay. Can we squish it up some more? I do believe we can. We can do pi, and we can do H cubed, and let's just do 27. there's a better way to write that. Let's do all of the constants out front. What about pi over 27 h cubed? Yes. So we have all the constants together and we have the variables together. It's going to be much easier to do. We haven't taken the derivative yet. All we've done is tried to consolidate a formula. So we still have to do an implicit derivative with respect to time. So when you do your derivative, you're going to have pi over 27 times 3 over 1 h squared dh over dt. Okay, let's bounce that up some. Now, the 3 and the 27 reduce. It gives me a 9 down here. So we've got pi over 9, and then this is going to be h squared dh over dt. Now, you don't have that many variables. You got dv over dt, you've got h, and you got dh over dt. And I have scrolled my problem off the page. So I'm just going to go through and I'm going to read this real quick. It says, if water is flowing into the tank at a rate of 9 cubic feet per minute, that is the volume. When it says 9 cubic feet, and that's how the water's coming in, so that's positive. 9 cubic feet per minute. That's the water that's coming in, total volume. Find the rate of change of depth, so that's height. How's the depth changing when the water is 10 feet deep? So this is the little snapshot of when we have 10 feet of water. So let's plug in what we know. Okay, at this little point in time, we know that we have 9 cubic feet per minute coming in. And we know we've got pi over 9 here, and we have 10 feet, and that's going to be squared. We're looking for dh over dt. Okay, so it's a little bit more cumbersome in the calculations, but that's okay. We need to square this out, and I'm working it with the units in there, but you guys can handle that. Y'all smart kids. So that's just going to be 100 feet, square feet, dh over dt. I'm just going slow. 9 cubic feet per minute. So that's going to be 100 pi over 9 cubic feet dh over dt. Okay? So now to get rid of that, because you're trying to get dh over dt, you've got to multiply by the reciprocal. 9 over 100 pi. Okay? So 9 over 100 pi. So when you do that, these cancel. And that was your whole little point, is to get rid of it. dh over dt. Over here, you just got to go with, think of that's over 1. So 9 times 9 gives you 81. And if this is feet cubed, that's on top. This needs to be feet cubed on bottom, right? Feet. Oh my goodness. You know what? I don't know. Let's see here. We'll come back and do the units here in just a minute. Let's just do the numbers for right now because I'm running out of time. Seriously, like I got like less than a minute. So that's going to be 81 and that's going to be 100 pi. This is a change in height over time, so we know good and well it's got to be feet over minute. And the question is, how in the world do you get there? I did say, oh, that's it. It shouldn't have been cubed anyway. This should have been squared. I was wondering how that happened. This is squared, so it should have been squared here. So this is squared, right? And it is on the bottom. And so over here, this would be feet squared. So when you reduce, you get 1 in the top over minutes. And so it works out perfect. Works out perfect. Problem was I copied wrong right there. Okay, so that's your final answer. Hope this helps. Y'all study hard and do a good job for your test.